Hello everyone, welcome to this lecture number 52 in the NPTEL course on Riemannian geometry. So, in the previous lecture I talked a little bit about fundamental groups. I did not prove anything, but I just reminded you of some basic facts and notions associated to the fundamental group. I will continue on this theme today and introduce covering spaces. Once again I will not give you any proofs, except maybe one small little argument. I will not really give you any proofs. The main idea is to sort of introduce or remind you of some basic notions from point set topology and algebraic topology that we will use in the rest of the course. Okay. Right. So let me talk a little bit about covering spaces. So again, as before, I mean this could be done for arbitrary topological spaces, but I am going to restrict attention to smooth manifolds. So then when we have a smooth manifold, one can talk about smooth covering spaces rather than just arbitrary topological covering spaces. So smooth, all our covering spaces are going to be smooth, right. So I will not keep repeating this again and again. So a smooth covering space or simply a smooth cover is a triple m tilde m mu, where mu is a map from m tilde to m, is a smooth map such that the following important property holds: for all p in M, there exists a neighborhood u of p which is evenly covered. Okay, so what do I mean by right, evenly covered by mu? So what do I mean by that? That just means that that if you look at the inverse image of u under mu, then that can be written as a disjoint union of open sets ui. So this is the disjoint union. Okay, where one, so this is a disjoint union, which means that ui intersect uj is empty for all I not equal to j, and the second point is that mu from ui to u is a diffeomorphism. Okay. So that is what we mean by saying that u is evenly covered by mu. And suppose so every point P has such a neighborhood which is evenly covered by mu, then we say that this triple is a covering space. So we call mu as the covering map, and sometimes we call m tilde as the cover of M by mu. Okay. So we will sometimes when we refer to a cover, we will refer to this triple m tilde m mu, or we will sometimes just call m tilde as the cover of M by mu. Okay. So we have the usual sort of standard picture, the stack of pancakes picture, or if you are in India, the stack of dosas picture, which is basically this. So you have this point P, there is this neighborhood u, and you have the m tilde here and this map mu. For each of these these points P in M, there exists a neighborhood u such that if you pull back that you have this sort of picture. So each of these is the UIs that sits above U. Okay. So UI is open in M tilde. Yeah. Sorry, just to be sort of consistent in the notation, I want to denote everything in M tilde by a tilde. So I should actually use a tilde to denote these open sets in M tilde. Okay, so this is UI tilde sitting inside M tilde. Yeah. Okay, so let me make a few remarks. So firstly, mu, it's clear, is surjective, and mu is also a local diffeomorphism. Okay, that's easy to check. The second point is that the inverse image is actually a discrete set. Right, because in fact the inverse image of P, so this is for all P, in fact mu inverse P intersected with any of these U tilde is a single point. Okay, so in particular it is a discrete set. And the third point is that even though mu is surjective and local diffeomorphism, the converse is not true. So the converse of 1, i.e. surjective plus local diffeo implies covering map, this is not true. Okay. So you do have a sort of converse which I will now state. So instead we have the following very important proposition. So let mu be a local diffeo then the following are equivalent. Okay, one, that mu is a covering map, and 2, mu has the curve lifting property. Okay, that is so what is the curve lifting property? That is, for any curve gamma, any continuous curve gamma with, let us say, P being the initial point, okay, and any P tilde in the inverse image of P, right. So let me say that this is a surjective local diffeomorphism, then the following are equivalent, right, and any P tilde in mu inverse of P such that right. So if you take a gamma with P equal to gamma naught and you take any P tilde in the inverse image of P under mu, then there exists a gamma tilde which is now a curve in M tilde such that gamma tilde of 0 is this chosen point P tilde, and gamma is precisely obtained by is the same as mu composed with gamma tilde. Okay, so the picture is the following: you have this M tilde to M, you have this map mu, Now a curve is basically a map from 0 1 to M. We say that M tilde has a curve lifting property if this lifts to a curve gamma tilde here such that this composition agrees with gamma, and so that you can specify the initial point arbitrarily. Okay. So having the curve lifting property is the same as mu being a covering map if you have a surjective local diffeomorphism. So one remark is that if gamma is smooth, one can smoothly lift it. So if a lift exists, then one can in fact define a smooth lift, and the second key part is that any such lift is actually unique. Okay. So what do I mean by that? So here's the claim. If gamma 1 tilde gamma 2 tilde are lifts of gamma such that they agree at the initial point. So both of them have P tilde as the initial point, then I claim that gamma tilde is identically the same as gamma 2 tilde. Gamma 1 tilde is identically the same as gamma 2 tilde. Okay, what is the proof of this? So let S be the set of all times t such that gamma 1 tilde of t is equal to gamma 2 tilde of t. So then clearly S is non-empty since 0 belongs to S, since the two lifted paths definitely agree at the initial point, at the initial time, and S is also closed, right, that is easy to prove. So my subclaim is that S is also open. In this interval 0 to 1 in of course the subspace topology, right, on the interval 0 to 1. Assuming this, then we are done. Since 0 1 is connected, okay, and any connected set, the only Klopen sets or closed and open sets are basically the empty set and the full set. So so this implies that S will have to be all of 0 1, or equivalently gamma 1 tilde is identically equal to gamma 2 tilde. Okay. So if we prove the subclaim, we are done. So let us prove the subclaim. Okay, so let T naught be a point in S, and let Q tilde be the value of gamma 1 tilde and gamma 2 tilde at T naught. Because T naught belongs to S, we know that these two values agree, so let us just call that some Q tilde, okay, and let the image be called Q. Okay. So then by the since mu is a local diffeo, there exists neighborhoods U tilde and U of Q and Q tilde such that mu from U tilde to U is a diffeo. Okay. Now suppose let delta be a small intervals be a small number such that the entire image of gamma I tilde of this set is contained inside U. So the picture is the following. We have this open set U. This is our point Q tilde. Now it might happen that these gamma 1 and gamma 2 might be different curves, but you can always select a small delta so that actually this extends in both directions, so that delta is small enough so that that entire segment of the curve gamma 1 and gamma 2 is completely contained inside U, right. This can be done because U is an open U tilde is an open set, right. Okay, now suppose there exists a T1 in this interval, in the open interval of length delta around T naught, such that so of course I can choose a delta small enough so that this intersected with, of course, the interval on which gamma I tildes are defined, this is completely contained inside U tilde. Okay. So suppose there exists a T1 such that gamma 1 tilde of T1 is not equal to gamma 2 tilde of T1, but then because mu is injective, it's in fact a local diffeomorphism, so in particular this is injective. If these two values do not agree, then the value if you compose them with mu, the corresponding values will also not agree. So if you apply mu on both sides, you get that this is not equal to mu of gamma 2 tilde of T1. But what is this? This is because both are lifts, this is equal to gamma of T1, this is also equal to gamma of T1. So that is a contradiction. Okay. So the upshot is that the entire interval T naught minus delta to T naught plus delta, the intersection with 0 1, is completely contained inside S, right. So so S is open. Since T naught was arbitrary, this proves that S is open and completes the proof of our claim. Okay, so that means as soon as a lift exists, it has to be unique, as long as you specify the initial point. Alright, that is good. Now I want to talk a little bit about the relationship between fundamental group and covering spaces. Okay. Right. So so the key observation here is the following. So the key observation is the following. Let us say you have your M and you have your point P, and let us take a loop at this point. Okay, so this is alpha. So let us say I have a covering space So then by the lifting property, by proposition, given a P tilde, there exists a unique lift alpha tilde whose initial value is P tilde. But now even though alpha is a loop, alpha tilde may not be a loop, and in general it will not be a loop. Okay. But because it is a lift, alpha tilde at 1 will still be a point in the inverse image. Okay. So this now gives you an action of the I mean, given any loop, you basically have found a way to transport P tilde to another point in the fiber over P. Okay. All right. So here is the key proposition about this. So let M tilde M mu be a covering space. Let P be in M, P tilde some point in the fiber above P, and suppose gamma 1 gamma 2 are two loops at P. So such that one gamma 1 of 0 is equal to gamma 2 of 0, which is equal to gamma 1 of 1, which is equal to gamma 2 of 1, which is equal to P. Okay. And suppose these are homotopic to each other. Okay. So let gamma I tilde be the corresponding unique lifts of gamma I such that gamma I tilde of 0 is P tilde, right. Then in fact the endpoints will also be the same. It may not be P tilde, in general it will not be P tilde, but they will be the same no matter you lift gamma 1 tilde or gamma 2 tilde, right. So this is the homotopy property of lifts. So as a consequence of this, one sees that there is in fact a transitive action of pi 1 of M comma P on the fiber at P. Okay. Because of this homotopy property, I mean, what is the action? You just take the lift. So let this be the unique lift of alpha such that alpha tilde of 0 is P tilde. Then we simply define the action of this on P tilde to simply be alpha tilde at 1, right. and the previous proposition, the homotopy proposition, implies the action is, so if you take two equivalent paths, then that gives you the same action. So the action is well defined. Okay. So this curve lifting property with this homotopy proposition tells you that there is a natural action of pi 1 of m on mu inverse of p. Okay. Right. So the final notion that we'll need in our discussion of curvature and topology is this notion of a universal cover. So before that I need to have a notion for when two covering spaces are identical or isomorphic. So we say that let us say m1 tilde m mu 1 is isomorphic to m2 tilde m mu 2 if there exists a diffeo psi from m1 tilde to m2 tilde such that the following diagram commutes. So mu 1 is simply mu 2 composed with psi, or as I said, the following diagram commutes. So you have a mu m1 tilde both mapped down to m via these covering maps, and you want this picture to commute. Okay. So next we define what we mean by universal cover. So we say that this triple is a universal cover if m tilde is simply connected. Okay. And then we have the following fundamental theorem on the existence of universal covers. So given an M, and this is actually the theorem that requires I mean this works on more general topological spaces, as long as your topological space is nice enough, I think locally path connected and a few other adjectives which are all satisfied if you are working only on a smooth manifold. Okay. So given M, there exists a unique universal cover. So unique of course up to isomorphism. Moreover, we have the following nice properties, that for all if you take the inverse image of P, then this is actually in bijective correspondence with the fundamental group based at that point. Moreover, we actually have pi 1 of M at P not only acts on mu inverse of P, but you can actually extend the action to all of M tilde. So in fact pi 1 of M, the fundamental group, acts on all of M tilde, and the action is of course smooth, free and properly discontinuous. So, all these adjectives imply that you can actually take the quotient of M tilde with respect to this group action, and that will give you another smooth manifold. The third point tells us that that smooth manifold is M itself. So, M is in fact diffeomorphic to M tilde modded out by this group action. Okay. Right. So maybe I'll stop here. Again, I have basically given you no proofs, but as I said, a standard reference for all of this material is Hatcher's algebraic topology. Okay. So this was just to give you a quick review of what fundamental groups and covering spaces are. In the next lectures, I will now describe this relationship between curvature conditions and topology in terms of restriction it puts on the universal cover and on the fundamental groups of manifolds with certain curvature properties. Okay, so that's it for this lecture. Thank you for your attention, and I will see you in the next lecture.